All right. Let's get started. There's lots of empty seats today. This is good. I succeeded in scaring a bunch of you away or boring you to tears or something. But the rest of you, we can enjoy our time together. This is lovely. And for those of you who are watching this on the internet, hello. Okay. So today, what I thought I'd do, and this is kind of in the spirit of a quick start to the class, was to get you just enough information both on how a database kind of could work and how you might write some simple queries so that you're, armed and dangerous to deal with at least one table at a time. So the whole spirit of the class, just by the way I like to structure it, is to front load material so that you kind of get your homeworks early, kind of get going early, and by the time we're midway through the semester, towards the end of the semester, this class is easing off in terms of workload, and you can focus on some of your other classes. So it gives a little bit of load balancing on the homework, hopefully. And also, just, when I took databases low many years ago, they spent a lot of time on, conceptual stuff, and it was a long time before we understood how anything worked or got our hands on anything. So I try in this class to, get your hands dirty right away. That was basically homework one. And then this lecture will kind of complete a short, skinny slice through sort of data management so that you can at least walk up to a database and be dangerous, okay? And also you can build some simple algorithms to do stuff like joins and hashing and sorting and things like that. So today we'll knock off single table queries in SQL, and I'll talk to you a little bit about sort of the query processing architecture that's typical in building data pipelines. And then next time we'll start talking about joins. And after that, you'll kind of have query processing under your belt, which is one of the first things you sort of want to think about or learn when you're dealing with large amounts of data. All right. So jumping right in, the goal today, basic SQL, which is sort of the standard query language that everybody continues to use, and then query executor architectures. So how do you build a query executor? Just a comment before we dive into SQL. How many of you guys know some SQL? Great. And how many of you ran into SQL because you had to for a job? And how many of you learned SQL for some other reason? Okay, mostly for practical reasons. It's a pretty little language. It's a domain-specific language for data. It's kind of reasonably well suited to its task. It's pretty old, and there's things that are kind of crufty about it. But for the most part, it's pretty good. How many of you know another query language, database query language? Okay, shout out the names of the query languages you know. Loud. Pig? Anybody else? There were some other hands up. Just shout out the name of the query language you used. HBase, okay. Has its own query language, I think. Yeah. Anybody use the MongoDB query language? A couple hands. Okay. Anybody used JSONic? It's a query language for JSON. Anybody used XQuery? Okay. So over the years, as different data formats and different data models have come out, people have tried to say SQL is old, let's not use it, let's come up with a new query language. And the new query language invariably looks like a somewhat cleaned up and usually made more complicated version of SQL, and then people end up devolving into saying, you know what, let's just build SQL again. So all the Hadoop vendors are building SQL, and a lot of the NoSQL backends are building SQL, and a lot of people have SQL layers over JSON. So even as we sort of evolve with technology, SQL is sort of an old friend of a language. You may not love it, but you're certainly going to want to know it, and it's handy. And it's more or less fine for a lot of things. It definitely has its quirks, and there's things you won't like about it. And for that, IBM apologizes, but hey, they invented it in 1975. Right. Okay, query executor architecture will be the second topic. Great. All right. So let's jump in. A little bit of relational dogma, and I don't particularly like dogma too much, but here's the way most relational databases have worked and continue to work, although there's some variation on this. Typically, in a relational database, when you define a table, you give it a schema, which is a description of the contents of the table in terms of the name of the table, the number of columns, the names and types of the columns. And that schema is typically fixed. We assume it's not going to change very often. You can change it over time. There's a command called alter table in SQL. You can add a column or drop a column or do things like that. But generally speaking, you can assume that the structure of the table is kind of fixed. And that's nice, just the same way that in a language like Java, you declare your data types and they have a particular structure. unlike, say, something like Python, where types can be looser, right? So this is much more of a structured, well-typed language, all right? So we're going to define the types of our tables up front. We call them schemas. So you have attribute names, and then each one of the columns or fields of the table has a type, and that data type in traditional SQL is an atomic data type. So it's not like it can't be an object or some kind of composite type. It's always like int or float or text or one of these sort of very basic atomic types. Now, most modern SQL databases will allow you to define more interesting types. You can have a column of type JSON, or a column of type set of something, or a column of type array of something. Those are all extensions to basic SQL that modern systems support. But sort of textbook database, and that's all we'll do for now, assume that the column types are atomic types, like text or integer or float. Okay. So the schema of the table is fixed. That's the description of the table. It's the metadata, the data about the data, right? But the instance of the table can change. An instance is a particular population of records in a given table. So it's like the state of the table. What data is in the table right now defines the instance. And the instance of a relational table is a multi-set of rows, sometimes called tuples or tuples, depending on how you like to pronounce it. So those are all synonyms, row, tuple. And it's a multi-set, which means you can have duplicate rows. So you can see here that Bob Snob with GPA 3.3 in the CS department appears twice. And as far as SQL semantics are concerned, those are two independent rows. They're different. They have unique identity. We have to remember that there's two of them. Okay, they're indistinguishable. There's really no difference between them, but there are two of them. Right? When we count things up, for example, we'll count that as two. So it's a multi-set, not just a set of these rows. Right? And every row has to fit the schema. Any questions so far? It's pretty simple, but you can imagine many things you might want to change. Yeah. Is there an order? There is, by default, an order to the columns, and it's the order you type in when you do the create table command, which we'll probably see later on. That order doesn't get used for much. You can, and it's usually not recommended, you can reference fields by position. You can, I think, say $1 or $2 for the second column or the first column. Definitely not encouraged. And the order can be changed with an alter table command, so also not a great thing to count on staying the same. But the names, people would typically not change the names of the columns. Why would we want multi-set instead of set? It's an excellent question. Does anybody want to try to give it an answer? I think it's debatable, frankly, but does anyone want to vote for why multi-sets are good? This is sort of a dorky example. Any of you have a data structure maybe where you feel like if you put it in a table it would need a multi-set representation? Or can any of you manage an application where you'd have two copies of the same row? I mean, for example, you might want to represent, this is maybe a silly example, but you might want to represent people visiting your store, and maybe in one table you have customer ID, product ID, just which customers bought which products. And I want to make sure that the count of rows in that store represents every time a customer bought a product. Turns out I buy toilet paper from Costco every 6 weeks, right? So it should have me in there every 6 weeks. It doesn't have the timestamp in that table, so they're not distinguishable. But we could still count up that table and get the right numbers. Maybe that's a bad idea, though. Maybe that's a bad design. Maybe I should have the timestamp there, right? Be able to distinguish them. So people debate about this. And don't forget, there's a perfectly reasonable set-oriented way to represent Bob Snob here. We could have said that there's one more column in this table, students. Try to write real big. So what do we have? We have name, GPA, department. And why don't we just have another column called count? And we can just keep track at application level. If we want to put a second row with the same values in it, would just bump the count. It would represent the same information, but every row would now be distinct. We'd have Bob Snob. He'd have a GPA of 3.3. He'd be in the CS department, but he'd be there twice. Right? Why not? I don't know. This is just the way it is. So what can I tell you? It's multi-set semantics. It's convenient for applications that are doing insertion logic. They don't have to think about counting. They just can pour stuff into the database. All right? And it is annoying for people writing queries, especially queries where you're counting stuff up or computing averages or other what are called aggregate functions, because you have to reason about duplicates. Do you want the duplicates when you're counting? Do you want to remove them before you're counting? SQL provides syntax to do all those things, but now you have to worry about it. Okay, so, and in fact, in our algorithms as well, we're going to have to define things like what is the union of two multisets? What is the difference between two multisets? What is the join between two tables that have duplicates in them? We're going to always have to think about duplicate semantics for everything we do with these things. And it makes the set logic just, a little bit more interesting. It's not that big a deal, though. Anyway, great conversation. Thanks for bringing that up. But it is the way it's going to be, multisets. All right, here's your basic structure, your basic structure of an SQL query. Anything in brackets is optional. So select column expression list from table is the minimalist SQL query, okay? But you can also add things like select distinct, which is, well, we'll go through these one by one. That's the skeleton. And what I'm going to do over the next set of slides is walk you through all the clauses and give you examples, okay? And this is pretty straightforward stuff. And I would encourage you, and we will along the way, I would encourage you to also get in and play with this stuff in a database, which you have in your VM, and I'll show you how to fire it up. Okay, so the simplest version, which is what's now not grayed out, is very straightforward. If you say select columns from table, maybe where something, you'll produce all the tables, all the tuples in that table that satisfy that predicate. And for each one of those tuples that satisfies the predicate, we will output one tuple with the expressions in the select list. An expression can be just a column reference, like I want to know the GPA column of the table. Or it can be an arithmetic expression over column references. I want the GPA times 2. You could also just plain old arithmetic. I want to have 17 minus 4 in every row for some reason. So let's look at some examples. Here's one. Select s.name, s.gpa from students S. Note the use of the variable capital S so that we don't have to type students over and over. We can assign it a variable. It's a little more convenient. Actually, in this particular query, you don't have to say the table name at all. Well, here, let me do the following. Let's read it out the way it is. Where this is a total typo. It got pasted in twice. I'm sorry. I think when I was editing it this last night, I messed it up. This should just be like that. And somehow it got pasted in again. There we go. This is finding the computer science students' names and GPAs, right? Get the names and GPAs from the students table where the department equals CS. That's all this was supposed to be. I don't know how that other syntax got in there. And so just for fun, let's try this in a little database I set up. You guys see that? Is it? I can make it bigger. I could also make it a different color. Can you read that in the back? It's good? It's good. All right, so really quickly, let's do a little cut and paste. Select s.name. We're in display mode. Got to get out of display mode. This part's easy. Actually, you know what? I have these all in a buffer. Let's do this. I have them all in Sublime. I also have some other stuff in Sublime. Here we go. There's that query we just looked at. s.name, s.gpa from students, where s.dept equals cs. Let's paste that into our SQL prompt here, and we get that out. Okay, you get the names and the GPAs for the students in the CS department. And just to confirm, they got pretty good grades, except for Bill. He dropped out. I think he actually got pretty good grades. Does anybody know who Bill Gates wrote his one academic research paper with? His advisor, Christos Papadimitriou. That's right. And so you can compute your Gates number, which is how many hops away you are as a co-author from Bill Gates. Happy to say I'm a 2, thanks to Christos. It's cool. Select star from students. Star is just a macro for listing out all the column names of all the tables in the query. So select star from students will show you everything that's in the table. So that's the full data set. And you can confirm, I think, if we go back to the previous query, that we got all the CS majors out and printed their names and GPAs. Okay? Great. All right, so that's fine. Let's go back to our examples here. So that's the most basic query you can have pretty much is select star from table. One step better is select particular columns from table where some condition holds. It's called a predicate. Okay. We can also remove duplicates by saying select distinct. Okay. And if you say select distinct, all that happens is we run the very same query, but right at the end, and remember you have to do it at the end because there can be no duplicates on the input, but duplicates on the output. So let's see this. Select distinct s.name, s.gpa from students for the CS department. So let's pull that one out of the buffer here and paste it into our SQL prompt. Okay, so that's fine. That's the distinct names and GPAs. That doesn't look any different, right? But what if we say select distinct s.gpa from students s? What's that going to produce? How many rows? Well, actually, where, sorry, we better do that. s.dept equals CS. All right, just 1 and 4, right? Make sense? So the duplicates are done at the output because when you project, which is to say just take out some of the columns, you may get duplicates introduced by that projection operator. Okay. So here we just projected to the GPA column. We had lots of duplicates. We deleted them on the way out. So select distinct, make sure that the output is distinct. Okay. We can also order the outputs any way you want, okay? And the order is done lexicographically, which means in your order by clause here at the end, you can do a whole list of expressions. Note that A2, which comes from the select list way up there, s.age times 2 as A2. So we have an expression in the output that we gave a name. We're using it in the order by clause. So you can have whatever arithmetic or stuff you want in the order by clause. It could be in the output like it is here, or it could not. You could just put in arithmetic in the order by clause if you're so inclined. Okay? But the lexicographic thing means we're going to sort by GPA, and if there's ties on GPA, we're going to sort by name. And amongst the ties on GPA and name, we will sort by this expression A2. All right, so this lexicographic ordering means you sort by the attributes in order, and then you break ties by looking at more attributes going right. Does that make sense? That's what the dictionary does with letters, right? The A's come before the B's, and within the A's, the second letter determines what comes before what, and on ties for that, the third letter determines what comes. It's like that, but it's with fields instead of letters, right? So it's nothing surprising. All right, and notice this as clause for naming output columns you can reuse in the order by. So let's just have a look at that real quick. Make sure that everything's working the way we expect. Hello, thank you. There's that query. All right. And there it is run. And you can see it's ordered by name. There's no ties on name, so that's not very interesting. But, well, let's just kind of, well, if we take out the name part, then we'll get some ties. Where are we here? Oops. Distinct. No. Oh, man. What happened? Order by, we got name in the ordering list, but there's no name in the output. So I think I lied, actually. We'll try that in a second. We'll see if I lied about something. That should work, right? We got ties on 4, and then they're ordered by A2, right? Now, I made an assertion before that you could put any expression you want in this thing at the end. So let's just try that. I may be wrong. Let's say instead of ordering by A2, we just order by s.gpa, square root of s.gpa, which is an absurd thing to order by. But it's not in the output, right? But are we allowed to order by that? And the answer is no. All right, so I'm sorry. I used to be able to do that in Postgres, but obviously it was illegal and somebody turned it off. So your order by expressions have to be in your output. I am wrong. Okay. Which is why we use that as A2 business. Okay? Excuse me. All right. By the way, there's lots of details like in any programming language in SQL. This is not going to be the kind of class where we're going to like quiz you on your SQL syntax and make sure it's letter perfect on a handwritten exam or anything like that. Like it's a programming language. We expect you to do live coding and consult the internet and all those good things. So don't get hung up if like what I just did, I should get no points off as a professor for not getting that right because I tried it. Now I know. And it's just like that's how you learn to code. So it's fine. Same thing should hopefully apply on your homeworks and exams. On your exam, we're not going to take off points for little syntax things and minor details. If you didn't understand something conceptual, like how to use distinct properly to get the right answer, that would be different. Okay. You can make your order bys descending or ascending by basically column by column, saying whether you want it to be ordered up or down. Descending is downwards, ascending is upwards. All right. And that probably isn't an interesting example to run, but it is legal. Okay, and then here's where life gets a little more interesting. This is computing aggregates. So in this case, I want to know the average GPA of students in the CS department. And I will tell you that in Postgres, the word average is actually not a supported keyword. It's AVG. And I think that varies from SQL to SQL. But that should be legal. So we'll try that query. I want the average GPA from students in the CS department. So let's first of all go back and look at the students in the CS department again. We'll just... And you notice a variation I'm doing now. I didn't do that capital S business at all. I just did dept, right? I said select star from students where dept equals CS. And it's implicit in a single table query that there's only one table you could possibly be talking about. So when you type in column names, it will assume they're from that table. And that's legal. Okay, so what I was doing with the capital S before was unnecessarily verbose for this particular single table case. So here's our students in the CS department. Their average GPA, I don't know, there's you can figure it out. There's 4 4s and 2 1s. But we can also ask our friend the database to figure it out for us. We'll say select average of GPA from students where department equals CS. Oh, it's 3. Okay. Is that really true? 16 plus 8 divided by 6 is, in fact, 3. That sounds right. Okay, good. So that's fine. Pretty simple. Let's make it more interesting. Before producing the output, what happened here, right? We took all the input rows and we computed a summary of some arithmetic expression, average of s.gpa, where the input to that arithmetic expression was a set of numeric values, right? And this is going to produce one row of output, in this case with just the one column of the average. There are other aggregates besides average. There's sum and count and max and min and standard deviation and median and a few other. Actually, there isn't median. Some systems support median. There's a few others, sort of simple statistical aggregations, all right, that you can compose together to do more interesting things. You can use distinct inside the ag function. You can say select count of distinct name from students, okay, and so it'll remove the duplicates before it does the counting. If you don't say distinct on the inside, it won't remove the duplicates. So just to be clear, let's go back here. Let's look at our students. I think Bill Gates is only in there once, but he's the wealthiest guy in the world, right? So he should be in there twice. Cool. So we'll say insert into students, values, Bill Gates. This time, let's guess that his GPA was 4.0, though. He must be older than 60. He's in the world domination department, and he is male. Okay. And you notice the single quotes, and you notice the syntax for insert into is pretty straightforward. I'm not going to teach you everything. So he's in there twice now. Oh, he's in there 3 times now. Awesome. If we say select count from students where name equals Bill Gates, how many should we get back? 3. Now, if we say count of name from students where name equals Bill Gates, how many should we get? 3. What if we say select count of distinct name from students where name equals Bill Gates? Now we get 1. Okay? So that's what the distinct clause does. And you notice that count is actually a special aggregate. You can put star in it, because it does, unless you're doing distinct, it doesn't matter what column you're counting. They all have the same number of rows. Most aggregates like max and sum and average, you need to tell them what column you're maxing or summing or averaging. Count. You just say count. But if you're doing distinct, you need a column name. Okay? And notice if we did this distinct on the outside, what does this do? Anybody? The second query, what's the difference with the second query? When does the distinct get invoked? On the whole output. So on the whole output set, we then remove duplicates. But the output set to this query is only 1 row, so it has no duplicates. So select distinct won't do anything here, right? So just to be pedantic about this, let's type it in. And you'll see that this is still 3 because there's 1 row. It contains the number 3, and it has no duplicates. Life is good, right? So the select distinct is done right at the output. You got to put the distinct inside the aggregate. Question?
Do the rows have to have all their fields identical to be duplicates?
They have to all be identical to be duplicates. So let's just hammer that home. Let's look back at our schema for students. Oops, that went by fast. So let's look at, say, GPA and age. Select GPA, comma, age from students. Okay, there's a couple of dupes in there. 4, 35 is in there twice, I see. So there's 11 rows there, and if we say select distinct GPA, comma age from students, there's only 9 rows. Yeah, so there were 2 duplicate rows before. But they have to be duplicate on all the fields in the output. Good. Okay, so those are simple aggregates. Now let's make this more interesting. I want to know not just for the CS department, but for every department, I want to know the average GPA. Right? Rather than having to run a query for the CS department and a query for the business department and a query for the English department separately, I can run one query that says select the average GPA and department name from students, group by department. So it breaks it into departments, and then it runs that aggregate query per department, essentially. Just to make this painfully clear, let's run it on our database. Where's our group by query? Here it is. All right. Right? And Bill Gates even made it in there with World Domination Department, and the average GPA there is 4. Now notice that the department field was in the select list, select average GPA, comma department. Okay. What if we said the following? Let's also ask for the student's name. Right? So I want to not only know the average, I also want to know the name of the student. That's a syntax error. You can read the error. It says it wants s.name to appear in the group by clause or in an aggregate function. Why is that? Yeah.
Because we're aggregating GPA, so you can have mapping.
That's right. So GPA, we're boiling it down to a single number per department. There's going to be a row per department, right? The department name is per department, so that's good. But the name of the individual isn't per department, right? What's the average GPA and name of students in computer science at Berkeley? Well, there's lots of you are computer science students at Berkeley. Whose name would we pick, right? It doesn't make sense. We need to construct a single row. Now remember that standard SQL doesn't have a notion of structured types inside fields. So it's not like I can take the set of all your names and shove that into the name field, right? I would have to somehow pick one string to put there. So basically it's illegal. The only legal queries are it's either in the group by clause, then it can be in the select list, or it's nested inside an aggregate function and it's getting boiled down to a single value per group. Make sense? I'm tempted to do something weird and just see if it works. I think Postgres has a crazy aggregate to accumulate a bunch of let's see if this works. It might not. My theory is that this is going to create an array of all the names in every department and put that in the cell. But I'm not sure if this is a default function in Postgres. And it's not, so forget that. Sorry, I tried. All right. Remember what I said, though? This query is illegal because name is not in the group by clause, and it's not nested inside an aggregate. Age is in the group by clause. Department is in the group by clause, so it's legal. GPA is nested inside an aggregate, so it's legal. All right. Cool. And that's exactly what we did at the bottom of the slide here. Okay. So, the general idea, you partition the table into groups. Each group has the same group by column values. You can group by a list of columns. So we could also say group by s.department, s.name, and then you get all the Bill Gates and the CS department grouped together, and the other people in the CS department would get different groups, right? So, for example, let's just do that. We're going to select the count, let's say, of department, comma name for students, group by department, comma name. So this is legal now, right? Because everything that's in that select list is in the group by list. So that's legal. What's the output look like? Well, it's department name pairs, because we asked to group distinct department name pairs. Right? So the group by clause, the more things in the group by clause, actually, the more rows you get, because you're slicing things finer. You're saying, I want more details per group. Now it's a department and a name. And you'll notice that there are 2 CS Bill Gates tuples, right? There's 2 Bill Gates in the CS department, so the count there was 2. Make sense? Can anybody identify? Does anybody know who all the people on the list are, just out of curiosity? Raise your hand if you recognize all those names and you could describe who they are. Most of them, I'd say all but 2 of them are fabulously wealthy. And the other two are important data people, let's say. So if you don't know who they are, you can Google them. And some of them are Berkeley alums, but I'm not sure how many, at least one. All right. Okay. Now, one more clause on group by queries that you can add is the having clause. Only makes sense if there's a group by query. It's a way of filtering output rows after group by that don't satisfy a condition. So remember, the where clause filtered rows, but it filters them before the group by. The having clause is going to filter groups after the group by. So this particular query, I want the average GPA and department from students, groups by department, but I only want to see departments that have 5 or more people in them. Okay? That's what that's saying. Now, you can't ask how many people are in the department before you group. You can only ask after you group, right? So let's just play with this query a little bit in the terminal. Here it is. I think because I didn't want to type in lots of data, I changed this to 3 instead of 5. But here's the query we looked at. All right, the CS department. And just for fun, let's make sure we also take in the count, so we see what the count is. All right, there's 6 tuples. There's 6 records in the CS department, and so it makes it to the output. All right, and the average for the CS department happens to be 3. Okay, if we got rid of the having clause, then we would see all the departments, including the ones with smaller counts, right? Okay, now let's change the query in a different way. Here's the having clause, but let's put in a where clause instead, or in addition. Where, and you'll notice new lines don't mean anything in SQL. S.name equals Bill Gates. Okay? So the where is being applied before the aggregation. The having is being applied after the aggregation. How many rows in the output? Can anybody guess? I heard 2. I heard 1. 0. Why 0? Sorry? Count is 3 is not satisfied by any department once we filter only to people named Bill Gates. Right? So the input to the aggregation is just students where name equals Bill Gates, which is the output of this. Oh, that won't work. Select star from students where name equals Bill Gates. That's the input to the aggregation. All right, there's 2 in the CS department and 1 in the world domination department. Then we compute the counts of that table and the averages of that table, and then we check the having clause on the output of that, and no department has 3 rows in it. Right? So where is applied before the aggregation. Having is applied after. In this case, the where leaves us with only 2 CS tuples and 1 world domination tuple, and none of the remaining groups have 3 things in them. Right? But if we change this to greater than or equal to 2, then we're good, because there's 2 Bill Gates in the CS department. Yes?
So where is applied before aggregation and having is applied after? Is that because of the nature of the keywords or where they're appearing in the
So the question was, for those of you who didn't hear, where is before aggregation? True. Having is after aggregation. True. Is that because of those keywords, or is it because of where they appear syntactically in the query? Let's say it this way. It is because of the syntax, so by definition, where is before aggregation, having is after. Also, syntactically, we don't allow you to say having until we've already seen a group by. So having has to come after group by. It makes it easier for the parser. Okay? It's part of the standard. I mean, we can try it, but I'm pretty sure it won't work. But let's give it a whirl. Having count star greater than or equal to 2. Yeah. It can't parse that. It needs having to be after group by. Okay. Where also probably has to be before group by. You can try that test at home. Okay. And the syntax in the slides is correct. You can optionally have a where predicate. You can optionally have a having, but the having has to be after group by. All right. Having can only be used in aggregate queries. It doesn't mean anything without group by. Actually, it can only be used. Let's try this. I don't know if you need a group by. Maybe you can just have an aggregate without a group by. So select count star from students. That's a legal aggregation query. one group by default, all the students, can you do a halving on it? Halving count star greater than 2. You can. Okay, so the halving only requires you to have an aggregate. Without a group by, there's only one group, and the halving is applied to that one group. So that is legal. Okay, that's fun. Questions up to here? Other questions? All right. So putting it all together, here's a query that uses everything we've learned so far. It's going to find departments, the average GPA, the count for females, group by department. I think we better lower the count because I didn't type in that many students. Order by department. Okay, so you can always order the output of any query, including an aggregation query. I know this won't work unless we say AVG because I tried it. Oh, and I have all sorts of gunk. 3. Sorry, this is the only one I didn't clean up last night, apparently. And let's make that actually greater than or equal to 2. So we get some output. Okay, good. All right, it's got to select, it's got an average, it's got to count from where. Oh, there's a syntax error there. You can see, we'll have to fix that. Where s.department. I don't know what happened here. Sorry. Some of my cut and paste died. There we go. I think that'll fix it. Nope. There's some messy text in here. Sorry. One more minute. Group by where s.gender equals f. Sure looks okay to me. Copy, paste. All right. I think it's just I think it's a screen wrap thing. No. All right. Well, I'm not going to type this one in. That will be homework for you because I don't want to type it in by hand. Sorry. We won't try to type this one in, but you can at home. You know what it's doing, right? Let's talk it through. It's going to take the students table. It's going to filter out only the females. We're going to remain now just the female rows from the students table. It's going to then group them up by department. And per department, it's going to compute the average GPA for the females and the number of females. Then it's going to throw away any departments that have fewer than 5 females. Fewer than 6, actually. And then it's going to get the output of that, which is going to be a bunch of departments with 6 or more females and the average and count. It's going to sort that by department alphabetically, and it's going to display that on the output. So where clause, and then group by and aggregates, and then having, and then order by. That's the execution order for that guy. Okay, and that you should understand the order of kind of how those are evaluated as part of your understanding of SQL. Okay, so I don't know if you can read this, maybe you can't, but you can try this in your class VM. So you just vagrant up, and then you can say sudo su space minus space Postgres, and you'll be in the Postgres account. And then you can create a database by saying create db test db. And then PSQL is that command prompt for SQL that comes with Postgres. Right? And then you'll be in Postgres, and you can do a create table statement and an insert. So I showed you how to insert the data in. And then you're off running queries. Okay. So if you, I actually strongly encourage you to do this at home. And so I encourage you to do it at home. Any questions? All right, so that's pretty easy stuff. That's just SQL stuff. So we looked at SQL. What we're going to shift gears now is look at software architecture. So that was just the kind of, I figured I should spend a few minutes teaching you some SQL. But we're going to go back now to designing software architectures, and in this case for database management system, query processing, all right? So any system that's doing query processing, you can think of a relational database. You can think about things like Hadoop or Spark, anything that's kind of doing pipelines of data through code is going to look more or less like what I'm about to describe, all right, with some variations here and there. But this is basically how you stream data through logic to generate more data. And pretty much all systems use some variant of what we're about to learn. Okay. Before actually we dive into that, though, let me give you a sort of overarching block diagram of what a relational database looks like, okay, so that you can kind of see the context we're living in for the next chunk of the lecture. So the sort of a traditional relational database kind of contains the following components. There's a database at the bottom that stores the data, and SQL queries go in the top, okay? And in between is the system architecture and all the software. So when a query comes in, it goes into something called the query optimizer that figures out the best way to execute that query. And we'll learn in this class what are the design decisions that the optimizer has to make. So what are the choices it can make to optimize the code, and how does it make its decisions. Once the query optimizer is done, it's going to generate what's called a query plan, which is the way that we're going to execute the query. You can think of that as kind of like bytecode for the query. And then query execution is sort of the master execution of actually executing that bytecode in quotes. What is that quote-unquote bytecode? It's the relational operators. It's these bulk data operations that we're going to be learning about in this class. You've learned two already, sorting and hashing. Those are examples of relational operators that might appear in a query plan. But we're going to string bunches of those together and then flow data through a pipeline of them, as we'll see in the next few slides. So what we're going to focus on today for the next few minutes is this execution layer, this part without the optimizer, and these relational operators, all right, which you've learned two of already, and we're going to learn more on Thursday. So mostly today we're going to talk about this part, this execution framework. The relational operators themselves might need to access disk, all right, like to spill things off to disk or to read things from disk. So they're going to have ways of going out to files, and some of those files may have special data structures on them, which we'll call access methods. All right, it's the code that allows you to access the data efficiently. Underneath those files, so to speak, those file access calls, and here's probably worthy of another picture, is something called a buffer manager, which is a kind of cache in memory. So imagine this is a whiteboard marker. Okay. Here's your disk. This is dead. Here's your disk. It might be an SSD. It might be a magnetic disk, but we'll just draw it like a can. Here is your code, so to speak, that's requesting data. Read next block of file F. Okay, there's some code in your system that wants to do that. It could go directly to the disk drive, but instead it's going to go through an API, and that API is going to check in a cache of disk blocks that have been kept in memory. Okay? So each one of these little rectangles here is the size of a disk block. Remember, a disk block is the size of thing you can ask for from the disk. So the disk delivers things in blocks. Let's say that's like 64 kilobytes. So each one of these rectangles is a 64 kilobyte slot in memory to hold a disk block. And that's what this thing is. And this thing's called the buffer manager. So these memory slots are called buffers. And the buffer manager decides at any given time what disk blocks to store here and keep, and what disk blocks, when you read a brand new one, should get kicked out to make room for the new one. Okay, so the buffer manager is a cache of disk blocks between the access methods for the files and the actual disk itself. And the last piece of software in here that we're missing is the disk space manager, which determines how to lay out the files on the disk drive itself. Okay, and it has to do things like reorganize things when there's free space. Maybe it also takes care of certain failure modes on the disk. But we'll talk about file layouts for databases as part of the class as well. So this is sort of a full stack in this rectangle here. It's sort of a full stack for a single user database. It goes from raw queries to raw disk IOs via query parsing, optimization, and execution, these operators, and all the file and disk access, and then brings the data back out. The piece that's missing from this picture is what's being alluded to over on the right, which is if you have multiple users using the database concurrently, we're going to have to worry that they don't mess each other up. So that concurrency control logic kind of affects all three of those bottom layers. The files and access methods, the buffer management, and the disk space management are all interleaved with concurrency control. All right, so we'll have to learn about that at some point. And then logging and recovery is also going to be a piece of this puzzle. So as you're doing IOs to the database and deleting things and adding things, we're going to also need to make sure that if kaboom, that disk drive explodes, there's a way to recover the data. And that's going to be done through a log file, and it's going to be on another device. So the logging and recovery component of the system is another piece that interacts, unfortunately, with all three of those things on the bottom. All right. So this picture you have over on the left is good enough to understand kind of a single user or isolated execution of a database. And if you want concurrent access, you got to do the stuff on the right. Your traditional relational database has all of that stuff. When you look at something like Hadoop, which many of you used in 61B, it pretty much just has the stuff here in the rectangle with parallelism, which we'll talk about as we go. Parallelism is actually easy, right? It doesn't have any of this concurrency control logging and recovery stuff that's traditional in a traditional relational database. I'll get you in a sec. So think of this kind of stack as sort of like Hadoop, if you will. Funny enough, NoSQL databases like Cassandra and MongoDB and things like that are kind of a horizontal slice from the file and access method layer to the right. So they don't include much of a query language typically, or the relational operators and execution, but they do some concurrency control and recovery, and some of this disk management. So it's sort of like Hadoop kind of went this way, and the NoSQL things kind of went that way and sliced the relational architecture apart. For simplicity, mostly, actually, in order to scale up. We'll talk more about Hadoop and NoSQL and all that later, but since some of you are familiar with it, I wanted to make sure that this picture, which is a traditional relational database picture, you get a sense that the systems you're interested in kind of fit into this picture in some way. Then there was a hand. Yeah?
When you talk about the buffer manager and the files, are these the same constructs that are provided by the OS?
Awesome question. So the question was, for things like the buffer manager and the disk space manager, doesn't the operating system do that? And the answer traditionally has been yes, but poorly. And therefore, the database system usually had to implement it itself in a way that was circumventing the operating system. By today, there's a little more cooperation. But still, because there's multiple OS vendors and multiple database vendors, the database system tends to do its own thing. And some of it has to do with this concurrency control and recovery stuff that relational databases like, okay, that the operating system typically doesn't have hooks for. So we'll talk about that at great length when we talk about concurrency and recovery and why the operating system doesn't do the right job for us. There's something also to do with this replacement policy in the buffer manager. Sometimes databases want to do that themselves as well. So typically what the database does is it circumvents the operating system one way or another, gets access to its own memory and manages it itself. Similarly with disk space. So like allocate a big giant file that's the size of the entire disk. The operating system doesn't know any better anymore, and the database works within that. Very typical. Right, this goes back to like Sun and Oracle not agreeing with each other in the 80s kind of thing, or the researchers in Soda Hall, like the database guy, and it wasn't Soda Hall, Evans Hall, the database people and the operating systems people, like the BSD group and the Ingress group didn't talk to each other enough. It goes back to those days, to the 70s. Could you have built it all together? Yes. The other thing I'll point out while we're on this little happy side comment is Windows tried to integrate the two. At one point, there was something that was going to be called WinFS, which was a file system for Windows that was supposed to be a relational database. And Billy G was all into this, and it almost destroyed Windows 7, apparently, because they just couldn't get it to ship and be fast at everything that the file system needed to be fast at. So actually, Microsoft made a valiant attempt to bring these worlds together in the early 2000s and failed. And depending on who you ask, they failed for political reasons or for technical reasons. So you can get many versions of that story, but typically they're separate. Long answer to a short question. Any other questions on this kind of high-level view of a database architecture, database system architecture? Okay. So today, as I said, we're focusing on a very small little slice, which is the execution of queries. Okay. So here's the deal. Actually, I just talked this through, but let's talk through the top pieces, really just the top box of that big rectangle. The query optimizer translates SQL to a special internal language. I called it bytecodes, but that's a sort of Java analogy. They're query plans is what we call them in database land. Right? And the query executor is, if you like, an interpreter for query plans. Now, there's a long tradition of saying, why would you interpret this stuff? Why not compile it to machine code? And you can do that too. And essentially what you'll do is you'll compile the kinds of programs I'm about to show you how to interpret. And that's fine. The compilation versus interpretation thing is kind of a detail. It's just as well to understand how the interpreter works. Essentially, you'll compile the executor with the query plan if you compile. So don't sweat the compilation thing. Think of the query executor as an interpreter for this query plan language. And query plans themselves are sort of you can think of them almost as a graphical language of these kind of blobs with data flow arrows between them. So it's going to show how data is going to flow through chunks of code. Okay? So each blob is going to implement what we'll call a relational operator. All right? And the edges in these graphs are going to represent a flow of tuples, all right, with particular columns. So every edge in one of these diagrams is going to have a particular structure, a particular schema associated with the tuples that flow along that edge. Every tuple will have the same schema along any edge in this diagram. So for single table queries, the diagrams are just going to be straight line graphs. So these are not going to be very interesting. In general, they could be trees or DAGs or even cyclical. You can have cyclical data flow queries that come in. That's fancy. We won't do that in this class. But for single table queries, it's super easy. It's just a straight line. So here's a picture of this query. Select distinct name, GPA from students. Give it to the optimizer, and it's going to spit out a data flow diagram that looks like this. I don't know if you can you read the letters in the back in this color? It's okay? Great, okay. So the bottom operator here is going to be a file scan. It's going to scan the students table. And as it starts scanning that students table, it's going to start passing records up. All right? And for whatever reason, it's customary to draw these things so that the data is flowing from the bottom of the page to the top. Okay, so these are sort of upside down if you think of them as trees, but that's the way it goes. The data is flowing bottom up. So data is going to start flowing out of this file scan, and the columns we're going to pull out of that file scan, the only ones we need are name and GPA, because there's nothing later on in the query that needs anything but name or GPA. So we'll throw away anything but name or GPA out of this file scan, and we're going to pass all those rows into a sort operator. That sort operator is the thing we learned last time. Right? It's that algorithm that takes a whole set of tuples, streams them into an input buffer, right? And starts sorting blocks of them and then putting them off into side files. So the left-hand side of that sorting picture is now this flow of data from the file scan. Right? So you just kind of wire that sorting picture into this file scan's output. And then the output of the sort, which again will just be names and GPAs, is going to be passed into a distinct operator. This operator's job is to see if it sees two tuples in a row that are exactly the same, it throws one of them out. Right? That's all it does. And it produces also named GPA pairs. Distinct, actually, there's a Unix command that does the same thing. It's called unique with the Q. So if you ever want to do this in Unix, you do it with pipes. And you can say this is equivalent to something in Unix that might roughly look like cat in lowercase, of course. Cat file, pipe into sort, pipe into unique. For these single table queries, you can think of these edges as like Unix pipes, and you can think of these operators as kind of operators sort of like those. Okay? Make sense? This wouldn't actually work, right? Because you'd have to say sort on what fields and unique on, anyway, but this is close. Right? So that's the kind of query processing that we'll see in these single table queries. It's very simple. And then this is just a picture, right? How do you actually make this like work? Like what's the code that you generate to make this work? So let's talk about that a little bit. In essence, this is a description of what we want. Now we need to interpret it. So the way we'll interpret it is every one of those operators will be implemented in our system in a class called iterator. All right? This is sort of a C++/Java ask bad object-oriented syntax, but bear with me. The idea is that every relational operator we're going to use is going to be a subclass of this class called iterator. Iterator has three methods: init, next, and close. And look at their signatures. Init doesn't return anything. It just initializes the operator. It says we're going to do query now. Get ready. Next is going to return a single tuple. Every time you say next to an iterator, it should give you back a tuple. And then close, it doesn't do anything either. It just says we're done. You can tear down your state. Okay? And it's going to have an array of inputs, which is going to be able to represent something not only like this picture, which is the picture we saw in the previous slide, but maybe something that's more DAG-shaped or tree-shaped, where you have multiple inputs to that iterator. So there'll be an array of inputs to the iterator, sort of left to right. What are all my input flows? Some subclasses of iterator will admit only one input. Some will admit two inputs. In principle, some could admit many inputs. All right? It depends how you implement your iterators. All right? Typically, in this class, we'll see iterators that take one or two inputs. Right? And then anything else you want to do in your iterator, you can obviously subclass it and add additional state. So the edges in the graph are actually implicit. Right? This is the picture of the data flow. But actually, the data structures are that there's three iterator objects, and this one has a reference to two of them in its inputs. That's actually what the data structure pointers look like. This class object points to this object and this object as its two inputs. But data is going to flow this way. Okay, so parents know about their children, if you like. Well, depends how you look at it. I guess children know about their parents. Children know about their parents, but the tree's upside down. How about that? Okay. Everybody good? Or did I succeed in confusing you? Iterators know about their inputs is the point, and those represent the data flow edges. And then this is all encapsulated in this iterator class, which means that if I'm, say, the sort iterator, I do not know what the type of the iterator is that's feeding me. So for example, in the previous picture, on the previous slide, sort was being fed by a file scan. Okay, so that's fine. So the tuples were coming in from a file scan. But if this thing wasn't a file scan, if this thing was like a gigantic query over 17 tables, that would be fine too. Sort doesn't care. It just knows it's getting a stream of name GPA pairs. Right? So nice encapsulation amongst our iterators. We don't need to know much from one iterator to the next. There's one exception that's on this slide. There's a thing we need to know. Does anybody catch me? I'm lying a little bit. Stump the professor. What did I say that's wrong? There is a lack of encapsulation in this slide. One of these operators needs to know something about its input. In order to do its job. Well, you only get 3 choices, and file scan doesn't have an input, so now you only got 2 choices. It's either sort or it's distinct. Which one of these things needs to know something about its child? All right, it's distinct, actually. Distinct, remember what I said. I said is if it sees 2 things next to each other that are the same, it ignores the second one. So it remembers exactly one thing, and when it gets a new thing, if it's the same, it throws the new thing away. If it gets a new thing that's different, it remembers the new thing and forgets about the old thing, right? So if I'm distincting a set, and you give me a 3, I'll remember the 3. If you give me another 3, I'll throw it away. If you give me a 6, I'll throw away the 3. Now I remember 6, etc. This only works if your things that need to be duplicate eliminated come in batches together. All the 3s come together. If you get a 3 and then a 6 and then another 3, I will have forgotten about my 3 and distinct won't do its job. So you need to have a grouped input to distinct for it to work correctly. Right? So if we sort, that's the reason we're sorting. We're sorting so that distinct can work. So there's actually sometimes a requirement, there's a little property of the class, which is like is sorted or is hashed, that will allow us to know that any duplicates will appear together. And that's pretty much the only property we're actually going to need for these guys, is a property that, the output of this thing is sorted or is hashed. By the way, as we write these things, different iterators will have all kinds of internal state, right? So for example, in sorting, if you do tournament sort, the internal state will include 2 tournament trees. And that'll be internal state to the iterator, right? It's in-memory data structures that the iterator keeps to itself, encapsulated. If you implement hashing, in the second phase of hashing, after you partition, when you bring it back, you'll have hash tables in memory, right? Or a hash table in memory. And that'll be internal state to the hash iterator, but it'll be encapsulated. Right? So different iterators will add additional state when they subclass this guy. Okay, here's an example of sort. So the sort iterator, it's got one input only. It only allows one input. And it's going to have a little bit of state. It's going to have a number of runs. How many runs did I generate on the disk? And then it's going to have an array of locations on the disk, of disk blocks, which are the locations where I put those runs. Okay? And it's going to keep track of the next record ID, RID, that it's going to deal with. And here's how the 3 methods will work in pseudocode. The initialization method for sort is actually going to read the entire input to the sort relation, every single row, and it's going to generate the sorted runs on disk. So when the top of the query plan sort of says init to the sort's not just going to do one little thing in return. It's going to say, okay, I'm going to initialize my child, which might be a file scan. File scan comes back and says, I'm all initialized. And then the sort's going to say, next, until it's gotten all the data out of its child and put it in sorted runs on disk. And only then will it return from the init to the top of the plan and say, okay, I'm initialized. And then when the top of the plan says next, well, then it's going to merge, and it's going to start producing outputs. All right? So this particular implementation of init for sort is going to allocate this runs array, fill it with disk pointers for all the places it put the runs. It's going to get number of runs set correctly, and it's going to figure out the next record ID array, which is going to be null to start with. All right, it's going to be all set to go. And the next record ID is going to be a pointer into each of the partitions, so it can do merging. So you think about merging two things, like zippering two sorted lists together, right? You need to know where you are in each list as you march down them to put them together. So that's what those next record IDs are. So the next is going to say, well, that next RID is going to tell us what we returned last time from our various sorted lists. And then when somebody says get next, we'll say, okay, here's all the pointers into my different partitions. Which one of them is the smallest? Whichever one of the smallest is the one that's going to go to the output, and we move it down, and then we put the thing in the output. All right? And then when you have nothing else to return, you return a special end of file, or since they're not really files, you can call it end of fun or whatever, up to the guy above you saying, I got nothing. You said next. I said, I got nothing. And then the guy above you eventually will say close, and you can deallocate all the data structures that you allocated in RAM and delete all the spilled partitions or whatever you had on disk and generally clean up. Okay, so that's a simple pseudocode implementation of sort. Hash is pretty comparable, so you can do that as an exercise. Pseudocode out what's the init for hash, what's the get next for hash. All right. Note that the next call and the init call, these are all synchronous calls. The iterator above you invokes init, and it's blocked until the init comes back, right? In particular, and this is kind of important, think about it like this. We have two iterators. This guy says, next. All right? That's a function call, like a traditional function call, which means that this iterator's state is now on the stack, and the next function of this guy is now running, and it will do everything it needs to generate a tuple, and the tuple will be returned on the stack to this guy, and then this guy will have control again, and he can say get next or return it to his parent or whatever, right? So one thing that's kind of interesting here in the iterator model is that control flow, which is to say which iterator is running when, is directly coupled to the data flow. Data is passed back on the stack so that if this guy's in control, it means it's in the middle of generating a tuple. And when it's done, it's got that tuple ready, it returns control to its caller, to its parent. Actually, this arrow should go like this, right? The calls go this way and that way. But the data flow is going that way. Why is this important? Suppose the control flow and the data flow were separate. Example, you have file scan like we had in the picture, right? And you have a sort. And I'm going to let them have their own control flows. So we'll give a thread to this guy and a thread to this guy, and they run separately. And the data is going to flow this way. What's the concern if they each have their own thread of control and they get to run at whatever rate they want? Is there anything that could go wrong? Yeah. Okay, so end conditions might be a problem, right? This guy's done long before this guy is, and he doesn't have a way maybe to tell this guy that he's done. But you could come up with a protocol, right? We use this EOF on the data flow. We could probably have an EOF here too, even though they have separate threads. I think that part's not so bad. But you're on track of something we should be concerned about. Yeah? Yeah, they are asynchronous, and we have no guarantees about who executes first at any given time, right? So this guy could be running 10 times as fast as this guy, or 10 times as slow as this guy, right? Because we're not controlling scheduling anymore. What happens if the file scan runs 10 times faster than the sort? Yeah? My buffer could overflow. I actually don't have a buffer in this particular picture. So this guy's like vomiting out tuples along this arrow. I don't know what this arrow is, but it better have some spare capacity to hold all those tuples that this thing is vomiting out while this guy's sorting real slow, right? So whenever you have these things separated, you have to worry about things like buffering, right? This guy's got to put things in memory so that this guy can get them at his leisure. It's a form of rendezvous, like we talked about last time, right? The handoff between this and this is made possible by having a little extra space. What if this guy's really slow? And the sorting guy is like really fast. What happens to the sorting guy? The file scanner's really slow. The sorting guy's like, I'd love to have a next tuple. What do you do about that? Has anybody ever written code with two threads that have to communicate? It's a producer-consumer problem, right? What happens if the consumer is way faster than the producer? Sorry? Starving. Interesting word. Yeah. So this guy would like to have data and he's starving for data. So what does he do? There's sort of two choices. Either he can do what's called polling, which is he keeps checking. He's like, got anything, got anything, got anything, got anything, got anything? Right? Which just kind of soaks up CPU. Or you can use the operating system or something like that to have him go to sleep and be signaled by this guy when he awakes. Right? But you need an external scheduler, like from the operating system now, to synchronize this guy and wake him up when there's something for him to do, which introduces overheads of various kinds. So this is actually kind of elegant, okay? Because we don't have any of these problems. This arrow only has to hold a single tuple. Where is this buffer in the iterator model? Where does this single tuple go in memory? It's on the stack, right? It's being passed back in return. It's on the stack, and it just comes back as the return to the function call. All right? The operating system's real good at that, and so is the chip. They optimize the crap out of that, okay? Because that's like your basic computer function call thing. So that's pretty good, actually. That's a pretty good thing. So this is all pretty good. Why might be a problem with this iterator model? Why might you want to have multiple threads going? Anybody think of a scenario where it would be a good thing to have multiple threads going? It'd be really lame to do this iterator thing. Multiple queries. Multiple queries on like different tables and stuff just have nothing to do with each other, I think. So that's okay. But it's an interesting theory. It's multiple something. You're on the right track. Oh, multiple threads asking the same table could be a problem. It might not be a good thing. So I'm looking for an example of something where multiple threads might be a good thing. So we're sacrificing it. This has a single thread of control. So I'm asking, the question is, when might that be bad to have a single thread? What's the basic reason you might want to have more than one thread? Yeah? Oh. Suppose you have multiple expensive operators, like this is slow and this is slow. What might you do to speed that up? Giving them each a thread is not necessarily going to make them faster. What might make them faster? Think outside the box a little. Think hardware. Throw hardware at the problem. Yeah. Yeah, let's have multiple processors. I'll put this on processor 1 and this on processor 2. I can't do that if it's a single thread, right? How many cores does your laptop have? 4, 2, 8, right? Seems like if you want a high-performance database engine, you don't want it all to be single-threaded on one core. That seems like a bummer. Okay, so hardware, multi-core, or even better when you have lots of processors, lots of boxes, like Hadoop kind of context, we're going to be dealing, actually, for sure, with multiple threads somehow. Okay, so today's a little bit simplistic. It's kind of from the era of a single core where this makes the most sense. Okay. Now, your operating system and a lot of other things on your laptop are not really taking advantage of multiple cores very well. Why is that okay for now? Why is it okay that like Microsoft Word is single-threaded and uses one core, which is probably false, actually, but let's assume it's true. Yeah. You don't need it. I mean, yeah, Microsoft Word doesn't use a lot of compute. So what do you do with the other cores on your laptop? You listen to music. You play video games. You have some process that's reorganizing your disk, right? There's all sorts of junk going on. So you just kind of say, well, everything will be single-threaded, but we can soak the processors with important background tasks. In a database server, that usually says, well, we have more than one user. It's a database server. It's fine. Every user will get a single thread. It'll be fine. And that's okay if you're running lots of small queries, and it's kind of bad if you're running one really big query. Okay, so there's a bunch of trade-offs here. When you're thinking about building the next infrastructure for your new employer after college, you want to keep in mind what your workload looks like, what hardware trends look like, and whether this is a good idea anymore. This single-threaded match your control flow to the data flow. It might be a great idea. Single thread per query, run like bazillions of them at once on really beefy hardware. That might be awesome. A lot of in-memory databases will do that. All right, lots of small transactions. It's all in memory. It all goes lickety-split. You don't want to do process and task switches and buffering. If you're building a Hadoop-like object, which is going to take a pass on a petabyte once a day, all right, you want to get lots of processors moving on that thing, and lots of data flowing through each one of them and all the CPUs pegged, which, by the way, Hadoop has terrible CPU utilization. But in theory, if it were well implemented, it would use up lots of CPU. So in that case, you might want to think about revisiting some of the stuff I'm talking about here. But for now, we'll just focus on single-threaded iterator model. All right? And the fun thing about this, just so you know, is that the code you actually write in it, next, and close, if I told you that this was, instead of being function calls, it was going to be, at the end of this thing, instead of saying return to next, you push the tuple into a send buffer to go off the network somewhere else, the code would be pretty much the same. Okay, so the basic idea here of encapsulating these things into these operators, the operators pass data between them, and the operators have methods to produce a tuple and handle a tuple, doesn't change so much when you change this control flow model. All right? But if all that seems like, wait, I don't really know what you're talking about, that's fine. Just stick with this for now. Okay? Stick with the iterator model and function calls. That'll be enough for this class. All right? Hopefully that was interesting to some folks, and if it confused you, what's in the slides is good. It's tried and true, and it's enough for this class. All right. Let's talk about group by a little bit. How do we implement group by? So we didn't quite do this. We came real close in class with sort, but we didn't quite do it. So the group by query is going to kind of look like this. There's going to be a sort operator, and then there's going to be an aggregate, or group by, if you call it that, operator. And here's how it's going to work. The sort iterator is going to make sure that all the tuples that come out of it are ordered by your sorting clause, okay, which is going to be the group by columns. So the query optimizer is going to take your query, it's going to generate a sort, and it's going to be sorted by the group by columns. All right? And then the aggregate operator, what it's going to do, suppose you said group by department. It's going to get a flow of tuples from the sort that's going to say CS, 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 data science, right? And the minute it gets a data science tuple, it knows it's done with CS, right? So how's this going to work? The aggregate iterator is going to keep running information on aggregate functions in the select list. So let's do a specific query. Let's make this concrete. Black is always a good color. Oh, let's not do average first. It's just one tiny bit more complicated. Let's do count. Select count star from students group by department. The sort is going to sort the tuples by department. Let's say the lowest alphabetical department is agriculture. Okay. So what we're going to need to do for count is keep the count so far of agriculture tuples. So it's going to start at 0, and then it's going to get an agricultural tuple. It's going to say, hey, we're doing agriculture. 1. All right, let's throw away that tuple. Get next. Get another agriculture tuple. 2. Throw it away. It's like I'm like the count. 3 agriculture tuples, right? And then you get a computer science tuple, and you go, 3 agriculture tuples, and you output 3. And then you say, 1 computer science tuple, And then you get next, you get another one, right? And you count up the computer science tuples, and then you output that one, right? And then you get data science, like output the final answer for computer science, then you get data science, you output that, right? So that you need this running state, count so far. For sum, that works too. You could have a guy named the sum. He wouldn't look like the count. He would look like anybody. He would be the sum buddy or something. And he would sum things, right? He would say, I don't know, GPAs don't add up very well. Whatever. He would add things, right? So he would keep adding things, and when he was done, he would have an evil laugh, and then he would output the sum. Average, well, average is sort of annoying, right? Because you need the count and the sum to do the average. So actually, even though this query says average of GPA, the running state of the aggregate is the count and the sum. And when you transition from one group to the next, you divide the sum by the count, and that's the average, right? So the running state may be more than one thing. For average, it's two things. That's fine. And as soon as the aggregate iterator sees a tuple from a new group, it produces output for the old group based on the final function of the aggregate. All right? And it resets its running info and updates it with the new tuple. Make sense? Pretty simple stuff. All right? You can even imagine an API for defining aggregate functions. You can make up your own. Right? It would have an initialization to say get started. It would have an iteration function that would say you're seeing a new tuple from the same group. And then it would have a final function that would say, okay, at the end of a group, what do you do? Right? So in the case of average, you divide the sum by the count. In the case of count, you just output the count. And so you can make up your own aggregate functions. And many database systems have an API for that, and Hadoop has an API for that. It's called reduce, right? And so on. So it's pretty straightforward to think about extensible aggregation. Have any aggregate function you like. Hash group by, a little bit different, but really not much different at all. Right? The hash iterator is going to be there. It's going to output its tuple to the aggregates. The only difference here from the aggregates perspective is that it's not getting its input in alphabetical order. So it might get zoology before it gets computer science, but the count really doesn't care. One zoology tuple, right? Oh, computer science, one computer science, right? So that's fine. Group by hashing works just fine. All right, but here's a funny thing. You can, we're done, right? So hashing is almost exactly identical to the previous slide. In fact, let's do a little visual diff. Oh, I didn't line them up. That's so sad. They're almost identical, and I forgot to line them up. So that the diagrams lined up, but the text got reformatted by PowerPoint. So sad. But almost exactly everything is the same, except it's not ordered, it's hashed, right? Okay, but we can do better, actually. We can do better with hash. We're going to define a single operator called the hash ag. It's going to do the work of hash and aggregate, but it's going to do it all at once, and it's going to get a win by doing this. So this is kind of cool. So what we're going to do is while we're doing our hashing algorithm, we're going to aggregate while we're hashing. So let's see how this works. We're going to first partition just like we always did in hashing. Right? So you take that coarse-grained hash function, and you generate output partitions, and you spill them to the disk. But when we read things back in from these hash partitions, rather than populating a hash table with all the tuples, we're going to read them in, and we're going to aggregate them as they come. All right? What are we going to build in memory for this partition? We're just going to build hash key, comma, aggregate state. So we're going to have an in-memory hash table. This is in memory, which is basically going to be a map from group by columns to ag state. We're going to use a hash function. It's our hash table, right? It's like a map from this to that, right? We're going to hash things into here as they go. So you read a tuple from the partition, figure out what group by columns value it has. So let's say it's computer science. Say, hey, there should be an entry in the hash table for computer science. Let's mark that down as 1. And the next tuple you get may not be computer science because we're just reading a partition off the disk. The next tuple you get might be zoology. That's cool. That goes somewhere else in the hash table, and that's 1. And then you get another computer science tuple, and you say, that's cool, that's 2, right? Right? You keep going, reading that partition off the disk, sticking it in memory, and bumping the aggregate. And this is all happening during the second phase of hashing, right? Previously, we did all the hashing, generated the output, and spilled it over to, passed it over to aggregation. Now we're doing the aggregate here. So my question to you is, why is this better? Can anybody see why this is better than just doing hash followed by, for each hash group, passing the tuples to aggregate? And I'll tell you, this could be like infinitely better. Well, maybe not infinitely. It could be way better. Maybe it could be way better. All right, I'll give you a clue. Suppose that what you're trying to count up is the number of males versus the number of females. And suppose I tell you there's 7 billion people in the world. So we have 7 billion rows, but all I really want to know is count of males and count of females. How big is this hash table in memory going to be? It's going to leave 2 entries in it, right? How big are these spill partitions going to be? Assume there's b minus 1 buffers, right? It's going to be the size of the input file divided by b minus 1. Each one of these could be gigantic. It could be way bigger than memory. If we do normal hashing, we have to build a hash table big enough to hold this thing, which it won't fit in memory, so we'll have to do recursive partitioning. And we'll, partition it and then do it and partition it and do it until we get it memory sized. In this case, with group by, if it's just male and female, it doesn't matter how big the input is. Generate a run of, actually, in that case, you could just do this all in one pass, right? You just read the data, and you generate a hash table of memory for male and female, and you're done. Right? So that's pretty cool. So actually, there's a way to even push this logic here. If it's small enough, if the total number of values fits in memory all at once, you can actually do your aggregation on the first pass, and it's just in-memory hashing. But if it's a little bit bigger and you need a partition, these partitions can be pretty big too. All right? And it all has to do with, the key here is the group by memory usage is proportional to the number of distinct groups. Whereas the plain old hash memory usage is proportional to the number of rows or tuples. And that could be very different, like if your column that you're grouping on is gender. Okay? So it can be a very big win to do hash and aggregation together. All right? So that's the main point on this slide. And I think we're out of time with that. Yep. All right. Homework is due tonight, as you probably know. Homework 1. Homework 2 will probably be passed out on Thursday. It's a partner homework, so you need to get your partners all locked down.